The Salar de Uyuni, the Bolivian salt flats, the flattest place on Earth, with less than 1 meter of elevation variation in 9,000 square kilometers. The largest mirror on the face of the planet. What if I told you that the Bolivian salt flats are actually curved and prove the sphere Earth?
Welling.
Big shout out to SCE Montreal. What a brilliant idea he gave me. He was talking about it a couple of weeks ago. The Bolivian salt flats prove the Earth is flat. It's so flat. It's flat all day. Flat as the eye can see. Flat, flat, flat. I decided to look into it. I did a simple Google search and I decided, what do I want to search for? Survey of the Bolivian salt flats. And let's call it Salar de Uyuni. That's its real name. This discovery is a hat trick. It's 3 in 1. It proves the curvature of the Earth. It proves the rotation of the Earth. And it proves gravity. 3 for 1. 3 in 1. And really, that was my original thought. But now I can see that it's more. It proves the horizon. It proves the sun grows below the horizon. In fact, the Bolivian salt flats, Salar de Uyuni, is the best place in the world to see the horizon and to see things going over the horizon. Much less refraction. Let's look at the article written on the survey, and then I'll pull up the actual survey itself. So let's get cooking here. Nature from 2007, even though they started in 2002 with the survey. So it was originally set up to help satellite calibration. The survey reveals a total elevation range of less than 80 centimeters. The precise topographical map has been made of one of the flattest places on Earth, the Salar de Uyuni, a vast plain of white cemented salt in the mountains of Bolivia. This is the southern Andes. The ground survey, aided by GPS, shows variation in elevation of less than a meter across an area almost half the size of Wales. Intriguingly, the work reveals bumps in the salt that lie above lumps of dense rock buried several kilometers below, just as water bulges over a bump in the ocean floor. Yeah, oceans are not all the same elevation. Knowing exactly where these bumps lie will help researchers to use the flat as a giant calibration device for satellite-based radar and laser altimeters. Adrian Borsa, a geophysicist of the USGS in Pasadena, led the work. It is now reporting the most precise GPS characterization of the salt flat, accurate to 2.2 centimeters. Borsa and his colleagues began the research in 2002 with a campaign that combined data from fixed GPS stations with the kinematic GPS data obtained by crisscrossing the Salar in trucks fitted with GPS antenna. It's as if you're on a white ocean with no waves, said Borsa. You see the horizon, the curvature of the Earth. It's absolutely featureless. Yeah, so There's two personalities, it seems, to the salar. You've got days where it's absolutely mirrored. It's just rained a bit. And you've got clouds in the sky. You cannot see the horizon. You can't even see up or down. You can't tell which way is up or down, let alone identify the horizon. But when it's dry and clear, it's the crispest horizon on Earth. It's as if you're on a white ocean with no waves, said Borsa. This study was commissioned specifically as a way to calibrate NASA's ICESat, launched in 2003, to study ice sheets in Antarctica and Greenland. Satellites can calibrate their altimeters by bouncing signals off the ocean surface, the height of which is well established. But because of atmospheric interference, tides, and waves, there are uncertainties. He said the salar, now accurately mapped with dry, clear skies, is about 5 times better than the ocean as a reference point. So, all you guys taking pictures of the horizons out to sea, this is the place you need to be. The results have been helpful, said Sinead Farrell, a researcher at the U.S. NOAA, who is using ICESat to measure changes in sea ice. It's the first calibration surface that we look at. The information that they provide is useful to all the other teams. She adds that the salt flat is also being used for ENVISAT, a European satellite. It must be part of Galileo, and could be used to calibrate future orbiters such as Cryosat-2, a planned European ice monitoring mission. Not so flat. Whereas the Earth-observing community likes the flatness of the salar, geologists are interested in the tiny undulations. The strength of gravity varies from place to place around Earth, imperceptibly to humans, but in ways that scientists have mapped precisely, owing to the density of objects nearby. So we get into mass attracting mass. So we'll see this on the geoid. Borsa found that the salt had created faint mounds of some 40 centimeters in height over regions of slightly higher gravity, owing to high-density volcanic rocks kilometers below. We found a rare breed of topography who says that this is the first time a land surface has been shown to undulate in step with the gravitational field like this. Here's a place where you can see the imprint of the gravitational field due to buried mountain ranges. Borsa has a theory as to how this happened. When the salar floods, as it does every 5 years or so, salt dissolves and in solution flows to regions of higher gravity. The phenomenon is already known to oceanographers. The freestanding ocean surface changes slightly match the pull of gravity underneath, so there are slight bulges in the ocean in places directly above the submarine seamounts. We know that the ocean follows the gravitational potential surface, the geoid, says Farrell, who is not a part of the study. It is a new result to show that the salt flats also follow the geoid. So here's an exaggeration of the geoid. Okay, it's more useful to look at it like this. The next step, for those with a geological interest, Borsa says, is to take out the portion of the elevation variations that are due to gravity and see what's left. So far, he is seeing a strange, regularly patterned checkerboard surface. This is useful. He doesn't know what could produce it, but speculates that it could reflect the imprint of periodic pressures due to the prevailing winds. Working out the forces could produce this pattern, could be useful in similar phenomena. If they're ever spotted on another planet, he says now we've got an analog on Earth. So the comment, I believe it was on here, and his name appears to be DLDR. No, the Bolivian salt flats are not an 80-mile Euclidean plane. Yes, these salt flats are very flat, but flat in this context does not mean like a Euclidean plane. No, it means without bumps or local variations in altitude. The surface of the flats represents a gravitational equipotential. Every point is, to an accuracy of a few centimeters, the same distance from the Earth's center. One interesting part of the article above is this. Borsa found that the salt had created faint mounds 40 centimeters in height over regions of slightly higher gravity, owing to high-density volcanic rocks kilometers below. We found a rare breed of topography. So volcanic rocks create higher gravity. Same time, land surface has been shown to undulate in step with a gravitational field. Here's a place where you see the imprint of gravitational field due to mountain ranges. Many flat earthers like to deny that Newtonian gravity is even a thing, so this is the perfect example of it. And Cavendish gravity. So right here, literally buried in the evidence you cite for the Earth being flat, there is a description of how scientists are making use of the unique geography of the area to directly measure the gravitational attraction of buried rocks. When you actually know some science and read beyond the first paragraph of pop science articles, you realize just how precise and detailed the measurements of people who actually do science are. People that actually do measure the Earth. Instead of being contrarians, and how much effort is actually put into mutually cross-checking and verifying the predictions of disparate scientific theories. Here's the actual paper from Harvard. That's a whole different article. Okay. When they measure altitudes, they're doing it relative to something called WGS 84, which refers to a spheroidal surface that is used as a standard to measure elevation relative to the gravitational equipotential that defines the ellipsoidal surface of sea level. This picture has to be credited to Diego Delso from Wikimedia. And so the sun comes down this way over the sky above and down below the horizon. Let's look at the actual scientific study. Summary: the Salar de Uyuni in the Bolivian Andes is the largest salt flat on Earth. There's a tongue twister. Exhibiting less than 1 meter of vertical relief over an area of 9,000 kilometers squared. We report on a kinematic global positioning system survey of a 45 by 54 kilometer area in the eastern Salar, conducted in September 2002 to provide ground truth for the ice cloud and land elevation satellite mission. GPS post-processing included corrections for long-period GPS noise that significantly improved survey accuracy. We fit corrected GPS trajectories with 2D Fourier basis functions from which we created a digital elevation model of the surface whose absolute accuracy we estimated to be at least 2.2 centimeters RMSE, with over 2 magnitudes better vertical resolutions than the shuttle radar topography mission data. This DEM reveals decimeter level topography that is completely absent in other topographic data sets. Longer wavelengths in the DEM correlate well with mapped gravity, suggesting a connection between broad-scale salar topography and the geoid similar to that seen over the oceans. Keyword: space, geodetic surveys, gravity anomalies, and earth structure, geomorphology, and go into technical details. Halite, 4 kilometers above sea level in the Andean Altiplano. And so they're crisscrossing with their trucks. And let's see. results and discussion. They're talking about all these different topography details that match the geoid where they expect it to be. Returning to the topography, figure 5b, we have to go back to that. We see that it's characterized by a broad ridge. Southwest, they identify all these ridges and characteristics. The higher density of the volcanic rock with respect to the surrounding sediments alters the gravity signal at the surface, resulting in bullseye patterns seen in the mapped gravity field. Bathymetry, derived from the satellite images of the flooded salar, has since corroborated our observation of a correlation between salar topography and gravity. While shorter wavelength, less or equal to 10 kilometers features of the salar DEM appear in the bathymetry. Longer wavelength and the overall slope of the DEM do not. Since water depth is the difference between the water and salar surfaces, and since water on the flooded salar nominally conforms to the geoid, this indicates that longer wavelengths in the topography conform to the geoid as well. Although the gravity field is not as smooth as the geopotential, it is similar enough to account for the gravity topography correlation we noted earlier. Is an unusual environment in that it is too flat to model as gravity-driven diffusion and has too little loose material available for mechanical transport to justify the use of standard models of sediment transport by wind or water. Instead, the transport of salt in solution is likely to be the primary mechanism by which surface change occurs on the salar, and we're exploring a simple model of salt transport, and that's going to be all digital. So, how fantastic is that? Beautiful, beautiful, great videos. And so what I found on good old wiki time is a lot of stuff. So watch this. Change it to Spanish. Boom. It's like double the information. I'm going to know the names of the waterfowl species. But that is the end of the flat earth and the end of my presentation. In summary, flat earth is already dead. I just like to kick the carcass around. You can go there. I would like to go there and show, instead of a boat going over the horizon, a van going over the horizon. Really, all you need to see going over the horizon is the sun going down below the horizon. In fact, that's what I'm going to do my next video on. So get subscribed and notified, and I will see you then. It's going to be on the sun and the horizon. I've created a synthetic horizon to model. Alright, see you then.